Hi guys, it's Mrs. Cerami. I hope you had a nice Easter spring break and I hope you're revved up for the lessons ahead as I'm really looking forward to teaching you again, even if it's just online. So we're going to continue with 9.4 today and we're going to do a do now. So this blast from the past is actually a, oops, I have to use a pen, is actually a do now because one, you need to understand how to get asymptotes. You just have to know that for next year. But also, we're going to be using how to find horizontal asymptote rules for the limits. That will help us for today's lesson. So this is a quick review. Vertical asymptote is, again, where the function's undefined at x. So in the denominator, you set the denominator equal to 0 because you want to know what value will make it 0, which cannot exist. So set it equal to 0. And solve. So x equals 1 is the vertical. Again, that's just the review. This is what we're going to be using today, these rules, horizontal. Horizontal is when you take the leading term from the numerator and you take the leading term from the denominator and you look at the exponents. This is x to the first and x to the first. If they match, then you just divide the coefficients and that's your horizontal asymptote. They do match. So we're going to have the horizontal as 1/2. Again, vertical, set the denominator equal to 0. This is a review from chapter 2. So if you need a further review, just go back to our chapter 2 notes. You can even go on to my math lab and do chapter 2 on there for study plan. And x will equal plus or minus 3. Horizontal. This is, again, the rules we'll be using today. Identify the leading term, 2x and x squared. This exponent is to the first and this is to the second. So the numerator is less than the denominator. When that's the case, then the horizontal asymptote will equal 0. And then just as a quick review, the third scenario, which we will see, if the denominator is higher than the denominator. So if the numerator is higher than the denominator, then it's none. It doesn't exist for a horizontal. Okay, how do we use that? Well, we're going to be talking about limit of a sequence. Limit of a sequence is when you have a sequence of numbers. It could be in the form of just numbers or in variables. And we want to know, what does that number go up to? It won't include that number, but what number would that go up to? So that's kind of like our horizontal asymptote. So if we look at this just numerically so you understand it, this is like 0.5. This is 0.6 repeating. This is 0.75. And this is 0.8. If we keep going, we're going to find that this is going to be close to, but not equal to. It's going to be close to 1. And that would be our limit. So if we ask, this is going to converge. Converge means that the sequence goes towards a number, a specific number, and we want to know what that number is. The number is 1. Now, if we write this with variables, 1, 2, 3, 4, let's make that just n. We notice our denominator is 1 plus the numerator. So we could just make this n plus 1. So again, if you evaluate the variables, you'll see the leading coefficients. We're going to divide them because the exponents are the same. 1 divided by 1 is 1. That's how we get that answer. Here, again, evaluate the leading terms. They have the same variables, so you just divide the coefficients and you get the limit of 2. And we can prove that just numerically. If you put 1, n for 1, this will be our n, and this will be our 2n plus 1 over n, just so you can see. You don't have to show me this chart at all. You can just tell me if it converges or diverges and then what it converges or diverges to. But just so you understand, if n is 1, then we're going to get 3 over 1, which is 3. If n is 2, we're going to get 5 over 2, which is 2.5. If n is 3, you're going to get 7 over 3, which is 2.3. You're going to see it's going to go very, very close to, but not including, let's say if we did 10, 2. So we're going to get 21 over 10, so it's 2.1. So it's going to converge to 2. So converge means, again, the sequence goes toward a number. The next slide, diverge. It means that the limit is infinite. It just keeps going. It doesn't stop at a number, or it could be non-existent. The non-existent we're going to cover in chapter 10. That's something I would prefer to teach in person, so hopefully we'll see you guys and I can teach you that. If not, you'll see that in the beginning of calculus. So again, don't freak out by all the variables. When you're identifying if it converges or diverges, you're just going to analyze the leading term. So, and look at the exponent. So we have squared over 1. So you could see right here that the numerator exponent is greater than the denominator exponent. Therefore, it must diverge. It does not converge. Okay, that's how I know it diverges, is that the numerator is greater than denominator. Here, the numerator is greater than denominator, it diverges. And again, you're not going to put a number it diverges to. Diverges means it keeps going and going and going with no ending. So there's nothing to do with that. It's only converge where you say what finite number it converges to. So here are just the general rules. You have seen these exact rules in this exact format in chapter 2. If the exponent of the numerator is greater than the exponent of the denominator, it diverges. So again, an example would be like n cubed plus n squared plus 1 over n squared minus 3n. These are the leading terms. The numerator is greater than the denominator, it diverges. If the numerator is less than the exponent of the denominator, so for example, if we have n squared plus 3 over n cubed plus 2n squared plus 1, this is less than that, then it's going to converge to 0. And if the exponents are equal, something like 3n cubed plus 4n over 2n cubed minus 2, it's going to converge to 3/2. It's the same rules as finding the horizontal asymptotes. We're going to do a few examples, and then you're going to work on just a few, both on my math lab and in the book. Okay, so here, I actually personally would not even focus on these numbers here. If they give you a general form, I would focus on just the general form. The leading term here is n, and the leading term here is n. They're both to the first power. Divide out and you get 1. And if you were to do it out, you would see it converge close to 1. If you put it in your graphing calculator, you'll see that it gets close to 1 as well. Here, the numbers just keep getting bigger and bigger and bigger. There's no way for it to actually stop anywhere. So this is going to diverge. And if you want to look at this, this is technically over n to the 0 power over 1. So the exponent in the numerator is greater than the exponent in the denominator. So that's how you could prove it as well. Here's the general form. So again, this is the leading term. This is not the leading term because it's not in the proper order. This is the leading term. Remember from Algebra 1, leading term goes from highest exponent down to lowest. So really we're evaluating 2n over negative 1n. The exponents are the same, so we're just going to divide and have negative 2. I think this is easier when you're dealing with decimals. I think it's easier just to write it as a fraction so you can actually see it a little bit better. This is going to be 4/10 or 2/5 to the n power. So technically, this is going to be 2 to the n power over 5 to the n power. Okay. Now, when we're looking at this, you can see that the exponent is the same. However, it's a variable exponent. So this is where it changes a little bit. Even though it's the same, you have a variable exponent. So if you look at this, if you do 0.4 to the first power, you'll get 0.4. 0.4 to the second power, you're going to get 0.16. It gets smaller and smaller. 0.4 cubed, it's going to be 0.064. And then let's do one more. 0.4 to the fourth power. This should really be in parentheses. You're going to get 0. I just realized I was recording and it didn't record. So I believe we ended here where 0.0256, and if you keep looking at this, it keeps getting smaller and smaller and smaller. Eventually the numbers will get so small it will get close to 0. It won't equal 0, but it'll get very close to 0. And you could, in your calculator, prove it. You could put something like 0.4 to the 100th power, and you'll see how small it is. And you'll end up seeing the exponential notation to the negative. So what this is here, my apologies, I thought it was recording, is that if you have a numerical exponent, then it follows the rule. If you have a variable exponent, so if you have a decimal or fraction to a variable exponent, it will converge to 0. This is a fact. Study this, memorize this, know this. If you have a decimal or fraction to the nth power, and it's a pattern, it will eventually go towards 0. Okay? So again, if you see something like this to the nth power with a variable, only if it's a fraction or decimal, it will converge to equal 0. Okay, now you're going to have about, I think it's 5 or 6 problems, some in the book, some in my math lab to do. My math lab will help you, which show me an example, and the book has the answers. Feel free to email me with any specific questions. If you're a Mr. Boland's student, feel free to email him with any specific questions. All right, welcome back. Have a good day, guys. Bye.